here. Thank you, Pedro, for inviting me here. It's my pleasure to be here. Great. So the title of the talk is Functional Programming, Object-Oriented Programming, and Algebras. Okay, so I'm going to basically try to give an overview of what I've been doing. And as Giuseppe pointed out, I do a lot of work in functional programming and also object-oriented programming with a focus on modularity. And one of the things that I found out useful in all the years that I've been doing research in this area is this notion of algebras. And this is what I want to tell you today. So, okay, so this is my long-term goal in terms of research. So how can I achieve modularity, type safety, and reuse? Okay. And also, so I want to answer this question, but I also want to do it in a particular way. I don't want people to need a PhD in type theory to be able to do this. So actually, I think at the moment, we already know kind of how to answer this question. So we already know a lot of how to achieve modularity and type safety and reuse. But currently, the solutions are still very involved. So they require a lot of very heavy encodings, and I think they are still not very useful. So I hope to share with you a vision of what can we do to try to achieve solutions that are easy and simple to use. Okay. So I'm not going to solve this question today, so this is my long-term vision, but I want to share this vision with you. So okay, that's my main goal for today. So let me start with some motivation, and for us to understand a little bit more about modularity and what do I mean by modularity. So let's look at the concrete example. Actually, currently I'm trying to develop a compiler. And so this is a compiler, and it's a compiler for a functional programming language. Okay, and if this language is it doesn't need to be very sophisticated, but if it's big enough, your compiler will probably have a number of different languages. So you might have a source language, then you might have an extended core language, then you might have a core language, and finally you might have some target language. Okay, so this is a typical architecture. Actually, in the current compiler that I'm developing, we have maybe 5 or 6 languages involved. And what often happens is that many of these languages tend to be subsets of each other. Okay, so you have a larger language, the source language, then something smaller, then something even smaller, and you make a number of transformations along the way. So one problem that you have here is that each of these languages requires a certain amount of very similar infrastructure. So here I show a very tiny example. So this is not actually proper language, but so this is just a simple language with arithmetic. So we have 2 languages actually. So we have one language that, for example, has numbers, addition, and multiplication. And the second language, the only addition is that it has negative numbers. Okay. So you could view, for example, negative numbers as being syntactic sugar that could be expressed just in terms of those. And this is actually a situation that you find often in a compiler. You might have a source language, and you might need to desugar some language constructs into some other language constructs. But let's say that you try to implement some functions on these languages. Maybe you need an evaluator, or maybe you need a pretty printer. So in a compiler, you probably need a pretty printer more than an evaluator. But in here, but you might also want to have an evaluator. But if you, for example, try to implement the evaluator, what you'll see is that you need to implement an evaluator for this language and an evaluator for that language. And the code is almost the same, except that this one here has a few more cases. Okay. So eventually, what happens is that you start seeing that you need to repeat a lot of similar code. So, okay, this one has numbers, that one has numbers, this one has addition, that one has addition, and so on. And ideally, what I'd like is to have a clear way in which I could express some of the relationships between these languages better. So, if one language is a subset of the other, maybe I can expect that I can use the pretty printer of the large language on a value of the smaller language, for example. And that way, I only need to write one pretty printer. So I write the pretty printer here, and that is capable of dealing with this language and also that one, for example. Okay. So generally speaking, my goal is to solve problems like this. And now getting into this talk in particular, so in this talk in particular, what I want to tell you about is that one of the things that I found useful, and not only me, but other researchers have also found useful to solve modularity problems like this, is to use the notion of algebras. And this is a recurring abstraction that shows up both in functional programming and also in object-oriented programming. And in fact, in recent years, what we have seen is that there are many different solutions to modularity problems like this, and all of them tend to involve some notion of algebras. So the goal that I have today is mainly, I want to try to give you an overview of this work and an overview of some of these existing solutions, and tell you about some of the lessons that I've learned. Okay, so what have I learned about these solutions? A second goal that I have is to try to show you that for those of you that maybe are not doing research in this area, but I want to try to show you that with algebras you can actually have a nice alternative to other language mechanisms like algebraic data types. Okay. And finally, I want to tell you a little bit about my vision of the future. My vision for the future, the key message, is that perhaps if algebras are so prevalent in all of these solutions, okay, perhaps we need to, instead of encode them, we need to provide some language support for them. Okay? And this will, my hope is that solutions that use programming, that have programming language support, will allow you to encode much more clearly and simply these solutions for these modularity problems. So, algebras. First of all, you might ask yourself, what do you mean by an algebra? It's a very broad term, right? So it's a very broad term. And actually what I mean in algebras in this talk is quite specific. So what I mean is essentially a variant of F-algebras. So if you work in data type generic programming, you are probably familiar with F-algebras. If you don't, you might still ask, okay, so that still doesn't answer my question. So what are F-algebras? Okay, so I'm going to start explaining a little bit of what F-algebras are. And F-algebras have been used for a long time in functional programming. And one place that you see them is in the definition of recursion patterns, like folds or cathomorphisms. So if you do functional programming, often you have to write folds, okay? And F-algebras are needed when you define the type, when you define folds. But essentially, in the 80s and the 90s, there was a lot of work in an area that I call generally the algebra of programming. There was a lot of work that basically made use of F-algebras to explain these recursion patterns, like folds or capomorphisms. So, okay, let's look at the simple fold. So let's suppose that you want to model a data type of integer lists. Okay, so you have a list with nil, cons, int list. So the fold of that list needs to take 3 arguments. This function here, this parameter here, and the list. What I mean by an algebra here is these 2 arguments. These 2 arguments are the arguments that you're going to use to replace the 2 constructors. So basically use this function to replace cons and this value here to replace nil. Okay? And this pair of these 2 functions constitutes the fold algebra of this particular data type. So a lot of the work in the algebra of programming was actually showing that these folds not only apply to lists, but they apply to many different data types. And then you get you actually get data type generic programming. So actually, if we had a different data type, we would have a different algebra, and with this different algebra, we could again write the fold for that particular data type. And F algebra is a variant of this fold algebra. So if you're familiar with ASCII fold R, the interface that you use is this one. So when you use fold R, you see something like this. You have a function here and another argument, and you use this function and this argument to replace these 2 constructors. But there's a kind of isomorphic representation of an algebra, which is called the F algebra, where this F here, so an F algebra has this form. It has some functor F, parameterized by a type A, and this is the input of a function that returns an A. Okay. So, for example, if you wanted to model the F algebra for our simple data type of expressions in ASCII, what you would have would be something like this: either int pair AA to A. Okay. And so this F here stands for the functor that you need. So F algebras are actually just this representation of algebras that use sums of products. So the first lesson that I want to tell you is that actually algebras show up in different forms. Okay, so you have seen we have folds written in 2 different ways. So actually in here I call this kata, and katamorphism was the name that people used in algebra of programming to refer to patterns like folds. But the important point here is that these algebras have various forms. Okay, so you have one form is the form that you see, for example, in the ASCII libraries. You see what you have there is basically a product of these functions. So you have an int. For example, for expressions, you have interval a to a to a. So that's one particular form of algebras. And the other form of algebras is this F algebra form where you have sums of products, okay, and then you use that in combination with the function. So the early research that involved algebras was essentially what I call this algebra programming, and algebra programming was essentially exploring the uses of F algebras in recursion patterns. So I want to go forward a little bit now, and I want to go to 2002 and 2003. This was about the time I started my PhD, and it was also the time that some researchers started doing some interesting things with algebras, which caught my attention. So one of the things was that they started using church encodings in interesting ways. Okay. So there were things happening in two different areas. One, in the functional programming community. The functional programming community was basically discovering GEDTs and the applications of GEDTs. Okay, generalized algebraic data types. And in a different area, more related to object-oriented programming, but also type theory, there was another work that was being done around this time. It was a type theoretic explanation of the Visita pattern. So the Visita pattern is one of the patterns that object-oriented programmers use. It's one of the popular design patterns. And it is typically used to, again, model tree structures or abstract syntax trees, and then do traversals on these trees. Okay. So, on the functional programming side, as I said, there were researchers at the time, they were working, especially the ones working at data type generic programming, which is a very dear topic to this workshop. What they were trying to do at the time was that they were trying to create so-called lightweight approaches to data type generic programming. So by 2002, 2003, what people were trying to do was to have some language-based approaches like polyp or generic Haskell, but then people realized that you could almost do data type generic programming as a library. So you actually didn't need to have some special language support. You could simply try to model data type generic programming directly in Haskell. So, and this line of work started around this time, 2002, 2003. And one of the key ideas that arose at that time was that one very useful thing to have was a data type of type representations. Okay, so this is one data type of type representation. So here, this data type has two constructors, and the first constructor is a representation for integers. So it's a very simple constructor. If you want to represent integers, you just need to say int. And this is a representation for product types. So if you have a product type, you can get its representation, but if you have the representation of the type argument A and the representation of the type argument B. So these representation types were useful to do a kind of reflection. So if you want to do data type generic programming, it's very useful to be able to reflect on your types, to inspect the structure of your types. And there were a couple of works that basically argued for these data type representations. The only problem was that at the time, Haskell still didn't support GEDTs. So if you know about GEDTs, you know that this is a special syntax that you have in a compiler like GHC that allows you to have algebraic data types where the return type is more specific. Okay. And so what people were doing at the time was that they were trying to encode these in terms of other features. One particular encoding of GEDTs was due to Ralph Hinza. And what he did was that he said, okay, well, I don't have GEDTs in the language yet, but I have type classes. And actually with type classes, what I can do is I can actually encode what is essentially the default algebra of the GEDT. Okay? So if you look here, you will see that there's a lot of similarities between this type and this type here. And the reason why they are similar is because this type class here is essentially capturing default algebra of that particular data type. So if you actually would try to write the fold for that data type, you would have to write something like this. You would have the fold would need to take two arguments, this rec int here, and then this second argument, which is a polymorphic function. Then it would take a value of the representation type and finally give you back this type. So this is this fold is a little bit sophisticated in the sense that you need a higher kind of type here, but it's still the fold of the GADT. So, as Ralph Hinze actually explained later on, so he first published a paper in 2004 where he provided this generics for the masses library, but then later on he published a journal version of that paper, and as he explained there, the essence of this encoding was type theoretics, the type theoretic encodings of data types, and in particular church encodings. Okay, so if you're familiar with type church encodings in System F, then you'll probably recognize some of the codes that we have written here. And type classes were just a clever way to do church encodings in Haskell time. Okay, so it was just a clever way to employ the features that we had at the time. And another thing that is not an observation by Ralph Hinze, actually other researchers have observed this before, but is useful in this context, is that church encodings can be viewed as a way to model algebraic data types using folds. Okay, so when you're doing church encoding, what you get is essentially something that gives you the fold of that data type. So that was the work in the Haskell functional programming community. But at the same time, as I said, there was a different line of work being done by two researchers in Cambridge, Bushlovsky and Tielika. And what they were trying to do was to provide a type theoretic explanation of the visitor pattern. So the visitor pattern was widely used in object-oriented programming, but it was mostly, it was a practical pattern, but people didn't understand it very much from the theoretical point of view. So what they suggested was that actually, at least some variant of the visitor pattern is can be viewed as a church encoding. So, for example, let's say that you would have a simple tree, like the tree that we have seen before, a tree with a binary tree with integers at the leaves and binary nodes. You could, the visitor interface for that particular tree would be something like this. So you have a visit for leaves that takes the integer argument and returns some type B, and then you have a visit method for nodes that takes two values of type beta and returns a value of type beta. And essentially, again, if we know about these relationships between church encodings and folds, we know that this is essentially the fold algebra of that data type. Okay? So, again, in this work, the essence was based on type theoretic encodings of data types. And the use of generic interfaces in object-oriented languages were just a way for them to model algebraic data types, if you wish, or to have an encoding of algebraic data types in an OO language. So, one second lesson that I've learned from this line of work is that algebras are actually useful to model tree structures in various different languages and paradigms. Okay? So you don't need to stick to functional programming or to object-oriented programming So actually you can use this idea of algebras to, in various different paradigms, and again, you don't need native support for algebraic data types in order to do so. So, yeah, this is just a summary. In all languages, we can use generic interfaces to model algebras. In Haskell, we can use various encodings. Type classes are just one of them. And actually, one particular application of this that is very popular these days is applying these ideas to embedded DSLs. So you probably heard of things like finally tagless in Haskell, and also maybe you don't know about these if you don't know Scala, but there's a similar kind of encoding in Scala, which is polymorphic embeddings of DSLs. And basically the idea of these two words is pretty much to take algebras and these algebra types and use them to encode the abstract syntax of an embedded DSL. Okay? And actually there has been some follow-up work that I think they are not using algebras anymore, but it's still a follow-up work of this, which is lightweight modular staging, which again is very popular in the object-oriented community now. And again, it comes from this line of work. So we step a little bit, and we come now to maybe 2006, 2007. We saw that in Haskell, the community was very interested in using these encodings because it allowed them to have a feature that they didn't have at the time, so GADTs. The whole community was also interested in this because they found a type theoretical explanation of certain patterns, and at the same time, or almost as a follow-up, people started applying this in perhaps surprising ways, like trying to apply these church encodings to DSLs and getting some benefits out of it. Okay. So, what happened after that? After that, we started seeing some more surprising applications, and applications that are useful in the domain of modularity. One particular very famous problem is the expression problem. So I'm not sure how many of you know about the expression problem, but probably quite a few. And what happened after 2006 actually was that many of the solutions that have been proposed for this problem, they all involve algebras in some ways. So just to give you a quick review of the expression problem, the idea is simply that, let's say that if you are using Haskell and you have a data type for expressions like this one, so you have binary expressions, maybe you have literals and binary nodes of expressions. A problem with algebraic data types is that you cannot simply go and extend this data type without coming and changing this definition. So it's not like you can come here and say data type with multiplications extends this data type here. Okay, so you don't have such mechanism in Haskell. So data types, algebraic data types are closed, not extensible in some ways. And so one problem with this is if you wanted to add multiplication, actually you would have to go and pretty much modify everything. So you would have to come here, add multiplication here, and then modify all the previous codes. Okay, and this is quite bad in terms of modularity. The expression problem, interestingly enough, also affects data type generic programming libraries, which was what I was working on at the time. Okay, and in particular, one of the problems with Rolf Hinze and many other approaches to data type generic programming, it was that they didn't allow extensible generic functions. So what does this mean? So you could write, for example, a serializer generically. So you can write a data type generic function that serializes some data type. But if you wanted to, for example, have an optimized version of the serializer for lists, you couldn't simply extend the generic function to provide you with a special case for the lists. Okay, so this is what I mean here by extensible generic functions. So this would be a useful functionality because maybe sometimes you want to serialize a particular value of a certain data type in a different way. And one of my first papers in this area was actually to come up with a solution for this problem for this generics of the masses approach from Rolf Hinze. And so I'm not going to show you the details of the solution, or all the details of the solution, but the main idea was actually that with type classes, you do have one mechanism for extension, so you can create subclasses. Okay, so if you have this type class here, and this is modeling the algebra for the data type of representations. If you want to have an extended algebra, say that supports sums, for example, you can just use subclasses to add a new case. And this was something that was quite interesting at the time, because this is different from an algebraic data type. In an algebraic data type, the definition is closed. You cannot extend it. But in here, with this particular encoding of algebras, I could actually extend the definition and add new cases without requiring me to come and change this definition. So I can do this without touching the existing definition. So the summary is that in this solution, algebras are encoded as type classes, and you can actually use the type classes mechanisms to extend the existing algebras. You just create a subclass, and this subclass allows you to add new cases. A little bit later, there was another solution that was proposed, which became very popular. So the data types a la carte by Walter Fiestra was an alternative solution to the expression problem. And interestingly enough, it also used algebras, but it used algebras in a different form. It used these so-called F-algebras. Okay? So F-algebras, as we have seen before, they use a sums of products representation. And again, the goal is not to explain you the details of the approach, but the approach also involves type classes, and it allows you to model F-algebras in a particular way. And like the approach in the generics for the masses, you can also add new cases. So you can also come, add a new instance, for example, if you want to have multiplication, and have new cases for multiplication. And there was yet some other solution. So I already knew about algebras and what they could do for extensibility, of course. So obviously what I tried to do was to apply this to object-oriented programming. So the expression problem is actually a problem that is not just for functional programming. It also exists in object-oriented programming. Okay. And so what I did there was, all right, I already know about this type theoretic explanation of the visitor pattern, and that uses algebras. Can we find a mechanism that allows us to extend, to achieve extensibility of algebras in object-oriented programming languages? And The answer is yes. So what you can do is quite simple. So you can model algebras as generic interfaces like this one. So this, again, this is modeling a simple tree with integers at the leaves. And if you want to add new cases, if you want to have some form of extensibility, all you have to do is to use interface inheritance. And basically that will give you the extensibility of the algebras. So I'm not showing you the full solution, but part of the core of the solution is this observation, that you can use these mechanisms to give you extensibility. So I showed you 3 solutions. Let's try to abstract away a little bit. Actually, 2 of the solutions, what they do is that they essentially use fold algebras. Okay, so this variant of algebras, like the folds that you have. And the way to achieve, and these fold algebras, they are essentially products of functions, which you can think of records. So that's what records are. Type classes are records. Object-oriented interfaces are records too. So you're using records to model algebras. And again, if you think of records as being products, okay, if you want to add new cases, you just need to be able to extend this product here. So in the case of data types a la carte, what we have is a kind of isomorphic solution. So they use a different encoding of algebras. This encoding uses sums of products. And what you need there is you need to, so you have these sums of products. Maybe the original data type is just with 2 constructors. If you want to add new constructors, you just need to be able to extend these sums. So you need kind of open sums. So the third lesson was that, okay, actually algebras, one nice thing about algebras is that they support extensibility and modularity. So with algebraic data types, for example, having new cases modularly is not possible. With OO hierarchies, adding new methods to existing interfaces modularly is not possible either. So one nice thing about algebras is that they come with some extensibility mechanisms that these other 2 mechanisms do not have. And basically that brings us to today. So today, we already know quite a few solutions. And actually there's a lot more work that is being done involving algebras. So maybe I can try to point out some of this, because unfortunately I cannot talk about all of it. But what people are trying to do now, for example, is to try to increase the expressive power of algebras. So one big limitation that you have of encoding data types with algebras is that you have to use folds. So if you know about folds, they can express certain functions, but many other functions are difficult to express. Okay? So one important question is, can we actually increase the expressive power of algebras? And it turns out that you can. So one of the works that I've done as a follow-up, for example, is to use algebra combinators. So you can actually use combinators to compose algebras, and these combinators pretty much look like zips. So you have zips of some 3 structures. And with these combinators, you can actually overcome many of these limitations. And for example, have operations that depend on each other. So this is one of the things that is already difficult to do with folds. But if you start composing your programs with combinators, then you can achieve this. And one very recent work done by some other authors, Thurman Randall and some other people at the University of Marburg, is again to extend the expressive power to allow you to model patterns that arise in attribute grammars, for example. So if you have, if you are doing language processing, you know that very often you need things like attributes. And what they are trying to do in this work that they are going to present soon is that they are actually trying to extend the expressive power of algebras to allow you to have attribute grammar computations. Another line of work that is actually orthogonal to what I've been doing in terms of modularity is ornamental algebras. This is by Conor McBride, and here he's trying to solve a different modularity problem. Okay, so it's the problem like you have lists, for example. When you start talking about dependent types, you might have lists, and you might have vectors of a certain size. And there's clearly a relationship between lists and vectors, but often what happens is that you need to duplicate codes between these two data types. You need a function reversed for lists, a function reversed for vectors. So ornamental algebras are, again, one way to use algebras to solve a different modularity problem. And another thing that I've also been looking at with some colleagues is how to do modular reasoning. So once we have these extensible components and modularized components, can we actually reason about them, prove properties? So then the challenge here is that the proofs need also to be extensible. So you also need a mechanism for the extensibility of proofs. Okay, so a summary of lessons learned. So lesson 1 was that actually F algebras, or algebras if you prefer, they show up in various isomorphic forms. So you have various isomorphic forms showing up around. Lesson 2 is that algebras are useful to model tree structures in different languages or paradigms. Okay, so 2 lessons. And lesson 3 is a good thing of using algebras to model tree structures is that you also get additional extensibility or modularity. And lesson 4, which is what the current lesson, is unfortunately the current solutions still require some heavy encodings. Okay. What I want to do in the future is actually to argue that what we want is to try to provide some programming language support for algebras. So at the moment we are encoding algebras. Okay, we have data types and we have whole mechanisms, but we are encoding algebras in terms of these mechanisms. And it's these encodings that make solutions very heavy. So you have to, as I said, you have to encode algebras with different constructs. Often you need to be able to compose algebras, but this composition, sometimes it comes for free. It's just, it comes just from the mechanisms of the languages, like subclassing, for example, but sometimes it doesn't come for free. And then you have to actually encode the composition operators themselves. And again, this becomes quite heavy. And another problem is that the encodings of algebras, they use parametric polymorphism or generics if you are using object-oriented languages. And in more complex algebras, for example, if you have a more complex system, mutually recursive data types and so on, what you need is, well, you need a lot of parameters. You need to do a lot of type parameterization. And again, this makes the whole encoding quite heavy. So what are the conclusions? So I think existing solutions using encodings have been extremely useful. I've learned a lot. With these encodings. And now I think I understand how to modularize systems better. So definitely using encodings has been useful. And I think we should also continue to explore these encodings to improve our understanding. I think encodings are very useful to improve our understanding and to discover new things. But what I also think we should try to do is we should try to not just encode algebras, but also try to create programming language support, come up with new language designs where actually you treat algebras and all the related infrastructure like composition operators and so on as part of the language. And I think this will be one thing that will make these modularity solutions much more usable from the programmer's point of view, okay? And that's it. Thank you very much for listening to me.
Thank you. We have some time for a few questions.
Hello, I've been using these kind of things, so I'm really looking forward to the future. How would you have language support for these kind of language?
Okay. So that's my current project. So I have one quick slide. I haven't done a lot. So this slide doesn't show a lot. So it's not showing. I think most of the issues actually show up later when you try to use client code. But it just shows some idea. I think one idea is that algebras, you can think of algebras or algebra interfaces as a kind of parameterized modules, a bit similar to what you have in the ML module system. So, for example, here the idea is that you are creating an algebra interface, and when you talk about algebras, you have sorts, which are the abstract types that you need to talk about. So if you're trying to create a data type of expressions, maybe you need a sort for expressions, and then you have literals and addition that you express in terms of these sorts. What I found useful, and again, this slide is it has some bias to object-oriented solutions, but in object-oriented solutions that I use, typically what you want to do is that you want to instantiate these sorts with some kind of interface. You can think of these as a record type. Okay. And so you could implement algebras like this. One of the things that I would love to have, so for example, if you use object algebras in Java or Scala, for example, this code becomes very, very ugly. But one lesson that we can take from the functional programming community, and in particular from data type, algebraic data types and pattern matching, is that you can use like pattern matching notation to very concisely write the cases for the algebras. So, as I said, most of you are functional programmers, but in the object-oriented solutions, this code would be quite ugly and heavy. So this would just be some solution that would make the code nicer. However, here it's still not showing many of the other things that get complicated, like composing algebras, for example, because you need to define your own composition operators very often. Okay. And again, my idea is that if you have language supports, you want these composition operators to be built in, so that you don't have to define them.
So thank you, Bruno. Lots of lovely ideas. No surprise that I appreciate any of the things you've been talking about. I'd like to channel Ole Kisseljohn. I don't think he's here. Yeah. So he's chastised me in the past for talking about church encodings, and as you've shown them, they're not church encodings, he says. their own Berarducci encoding because of the typing. So,
Right. So they are the typed versions.
Yeah, so we're missing Ole. That's
Right.
Ole. We're missing Ralph, and I think he'd say, so you were talking about composing algebras and sort of having sort of mutually dependent functions, folds, mutuomorphisms, we like to call them in the 1980s. So Ralph will say, they're all just folds, and it's all just algebras, and you're just restricting your attention to a single category, category ask. If you generalize to other categories, then exactly the same mechanism works. It's just a fold, it's just an algebra, and you just need to generalize the framework in which you're talking. So it's not an extension; it's just reading exactly the same constructions in a different set.